So yeah, you can interrupt me. I'm really eager to hear your questions. Actually, it's more than a paper. I will present a few things we have been doing with a group of people, applied to many things, and why I came to dynamic games. Because as Georges mentioned, I don't consider myself as a dynamic game expert. I learned, and I have to say that thanks to one of the surveys Georges wrote with Guillaumard and Jorgensen, I got to know many things, and of course I worked. But still, I'm discovering many things along the way, and you will see that clearly. Yes, I'm more a growth theorist and an optimal controller applied to vintage capital and infinite dimensional problems like age structures, etc. I started working on this, as Gustav know, many decades ago. So now I will present this paper, which is rather a program. Please interrupt me, I'm eager to hear you. So it's a program actually, which is more, much more, say, interdisciplinary than mathematical or anything. It involves people working on global problems like epidemics, like environmental, like global warming, basically, and management of natural resources. So in this team, I have famous people like Andy Dobson, a famous ecologist in Princeton, and mathematicians, which are probably less known because the mathematicians are always less known than others. Basically, the idea was to work on this global regional phenomena like climate change, pandemics, migrations, mobile resources, and our, say, obsessions are still three. We'd like to account as much as possible for heterogeneity, spatial heterogeneity, geography, technology, culture. Well, it's ambitious. You have to start with something ambitious and then you upgrade or you update. Second thing is mobility of factors. I think it's important. Could be for pathogens, could be for pollution, it could be local, it could be global, it could be anything. And the third thing, and we came to this and the last stage, that's why we didn't say go to dynamic games since the beginning. We came to this when we got interested into mobility, and we realized that we have, of course, natural mobility. We talk about this. And we have something which is not natural, which comes from purposive actions of people. And thus the dynamic games component, which came late. So that's an explanation of why I came late to dynamic games. So here I will present only the pollution part. I would say that the epidemic part, and Gustav knows this very well too, is extremely interesting, especially with the COVID stories. And we are working on a very big ERC project in which we use dynamic games on large populations using something which I discovered in the last years too, which is jeu à champ moyen. So that's, how do we call it in English? Because I'm working with people from Dauphine.
Main field games.
Field games, yes. So that's also extremely amazing. So here we talk only about pollution, global and local. So I think the link between the fact that space matters in the shape of pollution is an old thing. Everybody knows this. There are some excellent papers, some theoretical, 99% are empirical. For example, the paper of Henderson in the American Economic Review. And what we can notice, beside the fact that the majority is empirical, the overwhelming part of it is static. So they might have a spatial setting, but not dynamic. The second thing which is important, they have a very special treatment of pollution crossing one place to another. They use what they call transfer coefficients. The most elaborate paper I saw taking this approach is the one by Arnott. Arnott is a very famous guy. I think he passed away a few years ago. It's a fantastic paper in Journal of Urban Economy, static, but in order to explain how pollution moves from place to another, he spends I don't know how many axioms on defining a dispersion, pollution dispersion function. So one question we asked in 5 years ago, 6 years ago is, could we find something like a framework which allows for analytical studies? I mean, as mathematical economics, I need to prove things. I'm not happy with just simulations. So, and most of my colleagues have the same obligation, I think, moral obligation. So we wanted to develop analytical things, which allow to incorporate in the same framework heterogeneity, a large set of heterogeneities, dynamics, and something which is not ad hoc, specification of pollution dispersion, something which is natural. So that's what we wanted. The first thing we did, and then we published several papers on this kind of things, in which we have this spatial distribution. The second question, which is much more interesting, and that's why I will talk about this today, and that's why dynamic games will emerge, is the story of free riding, externalities, etc., which is typical in pollution, but also in other topics in ecology. For example, the coexistence problem in ecology. Barabbas nature is published in Nature is very important. The fact that you plant a GMO then crops, and then there is a drift there, wind bringing this to another place, and you have here cross-fertilization. Of course, it's not purposive, it's natural, but it's there. So it's a very wide problem, very important. But again, what we saw is most of the time, space is metaphorical. We have typically two country models. Spatial dimension is not there. That's what we see. And when the spatial dimension exists, as I told you, again, ad hoc spatial linkages in pollution. And of course, a large part of it is empirical. So that's the second thing on which I will talk today. Sorry to have taken 5 minutes to talk about the preliminaries. So we come to this. We, second stage, develop this objective. We want to develop comprehensive, but still, I say, average, tractable, spatio-temporal game theoretic frameworks to study the implications of free riding in the presence of spatial externalities and their natural diffusion, okay? And we want to develop this accounting for as much as possible for all the spatial and non-spatial heterogeneities. And then if we can do policies, things like this, that's even better. So, and then we looked at the literature, and we start with local pollution, and then we get to global pollution. So we will talk about the two things. I guess Fausto Gozzi did the same in Paris last week. But I'll have more time to talk about global pollution, which is the most important part of my talk today. So here, space is extremely important. And we looked at, of course, the papers which did this correctly. And we found a few ones. Fortunately, the first one we found is one of my former students, Barahona and Camacho, dos españoles, who did have their PhD with me in Louvain when I was director of core. And they have this natural pollution, this partial differential equation, this diffusion equation. And then, but they don't have games. The unique people we saw, maybe we are mistaken or we missed something, is papers by Guiomar and Javier, etc. And they have 3 papers like this, but they use numerical things. And we wanted something which is not numerical, as I told you. We wanted something which is mathematical, so that we can understand. There are many reasons why we wanted this. It's also idiosyncratic, but also, you know, the profession in economics is not the same as in operation research, etc. So it's a linear quadratic games is okay, but it's very difficult now to publish in top journals with this. So we went to this, to infinite, these problems, which are infinite dimensional, as you know. We have some notions of that. because we worked on infinite dimension. I worked myself on infinite dimensional problems since 25 years, so I know part of it. There is a literature there. Bensoussan is one of the best guys there. They have a technique we used in several papers, which is dynamic programming applied to infinite dimension. We can prove theorems. They are very complicated, so it's often 30 pages of proofs. But here it's really different. We are talking about games. And it's not only optimal control as we did 20 years ago. So we asked the question again, and we wanted to push this. Now, there are two things. One thing is you want to do something more realistic, like introduce something which goes beyond the typical modeling in economics. But at the same time, you have to convince economists. So I would take the first question we had to answer: how to convince economists that this law of motion is interesting? You see it here. It's the typical law of motion you can find in Camacho Barahona, which has been used in dynamic games by Guillaumard and Habir. If you present it to economists, I'm not sure they like all. I'm talking about economic theories most. So if you are not able to explain that you can reach with this specification something which allows you to explain better some important problem, then they will say it's too much algebra for nothing. That's basically what economists say. So what we decided actually to go for something more. So we saw what colleagues did, and I concluded from my own reading, because I'm more economic theorist than my co-authors. So I thought about justifying in a way the use of diffusion equations in these things by focusing on a problem which is very known in environmental economics, which is called the border effects. There are many papers published in very, very top journals like Lipscomb and Mubarak on the border effects for air and water pollution. Many papers on the US with the Clean Air Act, as you know, suggested a lot of papers on that. And these guys, Lipscomb and Mubarak, have a fully empirical paper which describes the border effect for water pollution over the Brazilian provinces, and they describe many phenomena like discontinuities and structural breaks at the border, but they didn't give any explanation for that. Why these structural breaks? Is it due for the natural diffusion? Is it due for intrinsic discrepancies between the neighboring provinces? Is it due to more economic behavior? Nothing. It's just an empirical paper, very well done for sure. So that's why we started with this. We started working on this, and I will shortly present why our paper in games and economic behavior, basically what it does is simply show that we can, with mathematics, without simulating, actually, it's just the numerical things there are just for illustration, not more. We proved how the use of diffusion while keeping tractability allows to explain many mechanisms there. So that's the first thing. Now for global, I will come back to this in a minute. Now for global pollution problems, of course, the problem is how to say it? Yes, the problem is quite different, because you know perfectly what happens. Wherever you are in Botswana or in Quebec or in Paris, the CO2 emitted will go to the atmosphere, or at least part of it will go to the atmosphere in matter of days, depending on certain physical conditions. So modeling the spatial transition or the spatio-temporal dynamics in the transition is absolutely nonsense. Is not interesting. So here you cannot convince me, and you cannot convince anybody that introducing physics here is interesting, especially if you have to introduce Navier-Stokes equations, which are very difficult to handle, but mathematicians know this very well. So here, two-country models are okay. We don't need to complicate more. The transitory spatiotemporal dynamics are not important. They will not help to explain any salient phenomenon or economic problem. So we go for two countries, but we insist that it's not because the spatiotemporal dynamics, the short-term dynamics are not important, that spatial heterogeneity is not important. Things about glaciers melting, of course, the consequences will not be the same in Bangladesh than in other places, than in Algeria, to give the example of my own country. So the spatial heterogeneity and other kinds of heterogeneities are still there, but we don't need a continuous spatiotemporal modeling. Still, the problem will be complicated because we'll have this. We would like to introduce physical, at least temporal dynamics for the CO2 coming out the planet. So this is what we do. Border effect for this local pollution, and we talk about this global pollution, global warming problem in two players, north-south game. The first paper, the first case is published. It's published in Games and Economic Behavior. I will go very quickly to save your time, and probably because some of you know it, so we'll go very quickly. I will present more with more, I would say, emphasis the two new things because we are like 5 or 6 working on that since 2018. I will present the two new things, a formal presentation of our methodology. I will do it in the finite dimension, but I can do it in infinite dimension, like we did it in Games and Economic Behavior 2022. And then I will talk about how we can use the technique to address the border effect problem very quickly, and then I will spend more time on the global pollution problem, the north-south model. Okay, so let me start. Unless you have questions, let me start with the methodology. So this I have to do to say. I owe a lot to the paper of Georges Guillaumard and Jorgensen, this survey I read 1.5 years ago, published in Environmental Modeling and Assessment. And then I discovered the class of games actually I was working on without knowing it. You know, this theater play by Molière. I was doing prose without knowing it. So that's basically I discovered this after reading this survey. So what I will describe here is the method we applied in all our papers so far, especially those in game theoretic setting, in order to come out with an analytical picture, at least to be able to prove some theorems and to understand the channels underlying some of the phenomena we want to explain. Here we are really targeting the identification of the effects coming from heterogeneity, from time discontinuities, from many other things, from also Knightian uncertainty, because the methodology allows also to treat radical uncertainty. I sent the whole monography. It's not a paper, actually. What I sent to Georges is a monography, which is unfinished. We are currently above 100 pages, so we have to decompose it into papers, or maybe not. So this is what we do. And as you will see, the method is not, the class of models I will treat are known. For example, Dockner. We are relying also a lot on the work of Dockner, especially his book. Actually, we took all the definitions, closed loop, etc., from his book. And we didn't know that he wrote on the class we are working on before reading the survey of Georges and Guillaumard. So it's linear in state dynamic problems, linear in state dynamic games in this case. So typically people use these models because they are tractable, and we didn't know that, actually discovered it. The paper of Dockner is precisely about tractability in dynamic games. I will come back to this in a minute. But what people do is typically to solve this is, as usual, Hamilton, Jacobi, Bellman, or Pontryagin, or whatever, depending on what they want to identify. What we do here is direct optimization. It helps a lot. It simplifies a lot. We did this because it helped us to get through the difficulties we had. If you use dynamic optimal control, I mean, then you cannot treat the discontinuities and the many complications we add in order to account for the things economists like to study. So, and we are able to find a way. Of course, the models are not easy. You cannot treat them as such. You have to identify subfamilies of specification and parameterization, which allow for this analytical picture. Hopefully, and we prove this in all the works we did, we can identify non-zero measure subfamilies in a sense that will be clear in a minute. So why I come to this? Actually, it's not my role because I'm new in dynamic games, but I saw a paper which was a bit arrogant. Say you can, it's recorded, it's okay. My talk is recorded, that's not a problem. By a guy who has published several papers using exactly the same technology, let's say, repeated games, and he was harshly criticizing dynamic games. And what really disgusted me, he was attacking Duta and Radner, who are fantastic researchers. And yeah, of course, these guys, I suppose they came to dynamic games because they wanted to study environmental agreements, and then they use linearities here and there. And of course, bang sometimes happen, and multiplicity also. But repeated games without dynamics, although these guys also claim these are the real dynamic games, without climate dynamics, for me, these are not appropriate neither. To study climate change, which is a dynamic, there's short term and there is a long term, and the long term is important, and you cannot understand it if you don't understand the short term. So that's my view. Then I discovered through the survey of Georges this literature, and I say, oh, we are doing dynamic games, linear in state, without knowing it. And then it's okay because we can design and devise big models with many heterogeneities. We can solve them without dynamic optimization, as you will see. And of course, there is no problem with these models because you can always, there's a degeneracy property. They are also, open loop is Markovian. There's MPs there. The economists are obsessed by MPs, as you know. There's one way to shortcut this discussion, which becomes to be a bit heavy for me. So that's it. And then you will see in a minute, we will transform the dynamic optimization into a sequence, an equivalent sequence. We prove equivalence. It's very important. We're mathematicians, so we prove equivalence. Equivalence is equivalent to a continuous time sequence of temporary, I use the word temporary for a reason, optimizations of problem where at each time t, the decision makers take their decision at time t, so static optimization, taking into account the expected future evolution of the state variables and their expected future marginal contribution to the payoffs. So it's like the Gromov, for those who know economic theory, the temporal equilibria of Gromov. It's in sequential trading. At every period of time, you have a static optimization, but accounting for expectations. That's what we have. And it's very easy to prove. Of course, it's not trivial because it's based on a non-trivial rewriting of the objective functions, the payoffs. You will see this in a minute, using a theorem we have all used thousands of times, Fubini-Tonelli or Tonelli-Fubini, as you wish. And then we take advantage, and I will show you this. So this is I promise I will not show too much because the idea is just to give you the intuitions. We can prove it for infinite dimensional problems. We did it already in the 2022 published paper. I give it here for infinite dimension, finite dimension, sorry. And then I will give you the intuition and the theorem. And then you will understand why a dynamic optimization problem can be equivalent to a sequence of static problems, because it's a bit shocking, without being transformed into a static problem, because I told you about expectations. Look at this. So we have this linearity in state. Everybody knows this. So we don't need to limit the number of state variables. So you have, look at the static question. It's, oh, you cannot see it, of course. You cannot see my... Le curseur, on le voit pas, Georges, hein?
Oui, oui, on le voit. We see
parfait.
it.
Tu vois, je suis ignorant. So this is the ordinary differential equation. So we have the things in Dockner. You have a linearity in state and separability. You need them to have tractability, full tractability. Well, full tractability, you will see. So here I can put all the linearity I want on the control. So we hardly have bang bang. The objective function, the same. This is multidimensional, so this is a scalar product. 8 is a vector, and capital AT is a matrix. Okay, and then you have in the payoff again separability between the state and the controls, and nonlinearity in the part of the payoff which depends on the control. And then I will come back to this in a minute. The technique is very quick. I will show. Imagine this is just a scalar differential equation, and this A is constant. Then, of course, you can integrate this equation and compute xt in terms of ut. That's an integral form. We agree on that. First step. You can express xt exclusively in terms of the controls, and of course the matrix AT will be there too. Then take this integral representation of the solution to the state equation and put it into the payoff equation. Then you have an iterated integral here. You have an integral here outside, and you have an integral inside. All the terms depend on capital AT, small at, and the functions involving the control. I would finish my job if I can transform the iterated integral into a double integral. And this is done by Fubini-Tonelli. Very simple theorem, which does not require simple thinking. Lebesgue integrability is the minimum, and then you have refinement, but in economics, that's not an issue. So at the end of the day, if you generalize, you have the typical thing. If it's a matrix problem and not necessarily an autonomous problem, it can be non-autonomous. This is very important for us to have non-autonomous things, because we think about bringing data into the problem, you see, and the data you can bring from a statistical institute. That's not a job I will do myself. I'm not at all an empirist. So that's something for them that's able to introduce your data. And then it's the typical thing which you can find you integrate. It reminds you, of course, in the case where A is this, the phi A is the evolution operators, and here's typically exponential of matrices in the autonomous case. And then you remember this. You can see it already. That comes from the integration when you replace it into the payoff equation, and then you have this. Look at this, my friends. This is BT. So this term will come after the Fubini-Tonelli, and it's simply the term which will bring expectations. You see T plus tau. So it's static optimization, but it's not static in the sense that we incorporate here the expectations about the future. Of course, it's a load because the problem is linear in state. I'm not overselling here. And then you have theorems like this, which could be proved. So you start with the problem I gave you. You replace, you use the static question, you integrate it, and then you use Fibini-Tonelli, and you can transform, you can rewrite your objective function exclusively in terms of current controls. I insist on the word current controls, and future evolution of the state, capital AT, the matrix AT, plus what I call marginal contribution to the payoff of the state. That's it. That's the technique. And then, of course, you optimize at every t, and you get the expectations there, and you reshuffle this at every time, and you can prove equivalence for the optimal control, and of course for Nash, for Stackelberg, for everything. That's in the paper, and George has the manuscript not finished. Okay, so that's what we do, and then we can talk about it. So what's interesting is that we can apply it easily. I insist on easily because you don't have to. You have to be big. All economists, even those who like mathematics, prefer to have static optimization than dynamic, even if the dynamic optimization is simplified by the linearity in state. But the most important thing is to have the possibility to study non-autonomous dynamics, which include discontinuities. We can have discontinuities in, for example, in parameters. It could be the case that the parameter in preferences in utility is equal to something before t, and then there is a jump there. It's not always difficult to handle with Hamilton-Jacobi-Bellman. So here we can do it because it's a sequence of static things. We can do it easily, I repeat. And we can do it, we can apply it to infinite dimensional diffusion-based problems. We proved it in the Games and Economic Behavior paper. And we can extend it to robust control, to radical uncertainty. As George has seen, we can do it too. The question is whether we put everything together or not. We use Hansen and Sargent and Minimax, so that's we can do it, and the extension of the method is quite easy. Also, the fact that we have the static optimization at every stage makes the manipulation of constraints like state constraint more easy, really much more easily. Yeah. And then I told you heterogeneity, of course. What's really interesting is, of course, you can do it also with Hamiltonians, but having this compact in single thing, and you follow it over time with the expectations moving, although they are exogenous, is more comfortable. And of course, we shortcut all the discussions on MP, etc., because these are typically, of course, we do not guarantee the uniqueness of MPs. We can prove it in the set of affine feedbacks, but that's I don't think we can require for someone who presents a theory, we can require that he has to ensure uniqueness of in games. That's so the argument of Harstad is a bit. I think if he gets uniqueness, it's because his model is very, very special. That's my point. Sorry to be so direct. And now that's the last point on methodology. And then George, I have how much time left? I'm talking a lot and I forget myself.
You have 25 minutes.
So okay, so I think I will.
Questions.
Yeah. So what I will do is to skip the local pollution problem and the border things because it's published, so people can see it. I can send you my slides for those who are interested. I can send it to you. I will move directly to the global.
Okay, perfect.
So yeah, so it's much better. So that we. So look. Then I come back to the assumption of linearity in state. Of course, I'm not oversell. I'm an old man, so overselling is not my. Of course, not all problems would support such an approximation. But in terms of realism, I mean. This said, I think our framework, if you, for example, you discuss issues related to heterogeneity, can move different heterogeneities there and make your experiments. That it's always informative. The other thing, I want not to push the ball too far. The other thing is that we maybe overstate a lot nonlinearity in many problems. That's my first job was to write algorithms, Newton-Raphson algorithms. Typically, the big economic models in which they are full with CES and things like this, if you choose the initial point not very far from the steady state, converge in 1 or 2 Newton-Raphson iterations, which means that they are not very nonlinear. So the story here, to make it short, if we talk about global warming, because that's a topic I will talk about in a minute, I will skip local pollution. There are many uncertainties there. I think whether for example, I'll give you just an example. It's a paper published recently in JIM, well, not that recently, 5 years. Dietz and Venmans. They study the outcomes of physical models and economic models on the on the relationship between the global stock of CO2 and temperature. So many people put logarithms, some power functions, things like this. I think we use logarithms ourselves. But if you look at the physical model, you see that the relationship between temperature and cumulative total anthropogenic CO2 is, well, I'm not saying it's linear. You cannot reject linearity so easily in many cases. So I would say linearity can be a good approximation in some problems. And in the cases where it's not a good approximation, I think the framework we propose allow for at least a benchmark investigation, exploration of some issues like those related to heterogeneity in, for example, in vulnerability to global warming or preferences or political power or the way people, okay, that's it. So let me go directly, forget about this. Let me go to the second part of the monograph. The third part is on robust control. I think there are not so many papers, dynamic games with robust control, and we have one there. We can do it because we rely on this very easy method, so we can do it. Let me go, well, take some time to discuss a few things here. So here it's global pollution, so we don't need to discuss here the short-term, the spatial dynamics in the transition. We have 2 countries, north and south. 1 is for the north, 2 is for the south. They have a utility function there, which depends on consumption. And the S there is the typical notation for the stock of CO2. S bar is the level at the beginning of the Industrial Revolution. This is a typical notation. So here it's an example that this is just an application of the method. Of course, we have these constraints. That's, remember, linearity in state and separability, additive separability. We need it. Now we can spend, I don't know how many minutes discussing where to put the damage function. This very big man, Martin Weismann, wrote so many papers on that. You can put it here in the utility function. You can put it in the capital stock accumulation. You can put it in multiplying the production function. You can put it everywhere, and we can put it everywhere, although we cannot put it in multiplicative form. We have to put it in additive form, and nobody can convince me at the minute that multiplicative is better than additive. I think to model what's going on, given all the uncertainty we have and all the choices we have. It's a very complicated question, where to put the damage function. So here is just an example. I put it here. Second thing, I will now review 3 technological assumptions. One is about production. Here, we are a bit inspired by the paper of Golosov and others in Econometrica 2014. And in order to simplify a bit, to have just 2 static questions, if we add capital accumulation, that will have 3 static questions. already have two. You will see the two static questions in a minute. We suppose that here we don't have capital accumulation, or if you want, full depreciation of capital. So the I there is input. Since it's an input, it's a control. Here you can put any nonlinear form. It can be Cobb-Douglas, like in Glossov. We're not put Cobb-Douglas, but it could be Cobb-Douglas. You know the technique. The linearity are to be imposed only on the states. The second thing is we have production and we have depollution. So the B here is the abatement effort, and DI is the resulting depollution or abatement of molecules in country A. You see that technological progress here are exogenous. This is the technological progress in production, and this is technological progress in depollution. It's important. Every country, north and south, has its own level of technological progress. It's an important part of the story. This is one of the most important stories actually now in the negotiations, how to compensate the south. And then the second type of assumptions is, I think, is about, here you see how we introduce non-autonomous equations. We assume that, well, we could actually. It's not really, well, it is non-autonomous because, so we assume that the frontier is at the north, so the TFP in the north is maximal. We assume it follows a certain trend. It can be constant with or exponential as you wish. And then here comes part of the interesting story we have in this application of our method. We assume that the south is catching up, and that's A2 follows a certain catching up equation, but this catching up equation can be accelerated thanks to a transfer RA from the north to the south. It's a control variable in the hands of the north. Okay. Of course, there is a function H here has the same typical properties of catching up equations in growth theory. And the same thing for the abatement. We assume that the technological frontier is in the north, and you have a catching up equation here. And then you have a second type of transfers, which is transfer to the depollution, to the abatement technology. Okay, so we have these two things. Again, it's in the hands. It's a control in the hands of the north. That's what we have. Okay, and then we have the static question, the climate model. That's why I'm a bit angry when people claim that they're talking about global warming and they don't have a climate dynamics. So it's completely disconnected from what's happening in the physical world. So here we take into account this part. It's a simplification of Nordhaus. I prefer by far Weismann, but I'm following the rules of this profession. Let's use a model which is more popular. That's this one. I'm not at all impressed by this paper, but it is there. Okay, so what we have is two stock of CO2 emitted by, in my case, only by production. And then you have part of it, which a fraction phi L, you can see it here, which goes to the atmosphere. Yeah, sorry, I didn't define this. G I1 plus I2, remember I1 is input used for production in the north, this is in the south, and this is the pollution. So this is net emissions, okay? Total net emissions. So these emissions, part of them, phi L, goes to the atmosphere, it becomes permanent. The other 1 minus phi L remains in our planet. Part of it escapes into the biosphere, and the rest is decaying at rate phi. And then ST is the sum of the two. I don't know if you know this model, but it's, you see, that's why we didn't add capital accumulation. We have already two equations here, and then we have to, it's an application. If it were really a real application to real world, we would have introduced capital accumulation. Then for institutional arrangement, We thought it was interesting to test two kinds of central planner. A central planner without national sovereignty constraints. That's the guy can move production from a place to another on closed production in a country and just produce in a place. That's a typical superpower, super powerful planner. And another, basically the guy has a single budget constraint to respect, his or hers. And here you have a central planner who has to respect that he cannot move production from a place to another. He has to respect the budget constraint of each country. And then we have Nash and Stackelberg. Stackelberg, where North is the leader. Here I will just present the three first one very quickly, but I hope I show you the kind of models we can treat here. I introduced this complication. We can talk about several things here. I introduced purposively this non-autonomous features. I introduced two kinds of transfers. I think it's an important question. I have not seen it treated, at least in this kind of north-south framework, theoretically. I mean, I'm theorist. So we do this, and let me show you. I was claiming that we have a method which can produce analytical results, at least sometimes closed form results. In other cases, it would allow us to prove theorems. I would be happy if I can prove theorems without having the closed form solutions. So this is one of the classes which allows to have analytical results. And as you can see, we can take any utility function, which is typical isoelastic. Here you can take any power functions, if you wish. And then you basically here for net emissions we took something like this, and then it can allow to produce explicit solutions even. So this, in this sense, it's not. I don't know if you are not growth theorists, but Gustav knows this theory. The typical case in a Ramsey model in which you have an explicit. I'm talking about a Ramsey model. That's just one control C and K. Is to have logarithmic utility function and full depreciation of capital, my friends. That's the unique case in which you can have explicit solutions. Here, you see, we are going much farther. So let me present some results. I think in 5 minutes I will be done. I think 5 minutes or 10 minutes. Let me just check. Yeah, 5 minutes, I promise, George. So this is the planner without sovereignty constraint. As you can see, the guy is optimizing everything. The controls here are C1, C2, B1, B2, RA, RB, I1, I2. And then the objective function is the sum. And then you, of course, if I ask you the question, what would be the optimal behavior of this guy, knowing that one region is more polluting than has a disadvantage in pollution, of course, he will close the production. Look at this, I2 equal to 0. He will close production in the south, only production in the north. And he will, or she will, sorry, she will not, of course, because precisely production is closed in the south, he will not or she will not subsidize transfer to production, but possibly to abatement, because you know that planting trees in the south helps also, you see. So this is the typical stuff. I just want to mention that if you look at the formulas, you might see that they are constant. Of course, they are constant because the technological frontier is constant. If it were not constant, then it will be. But that's not an issue. The thing I wanted to show you is this parameter phi, because you could tell me, and you would be right, where is the dynamic here? What are the expectations? Where are what is the physical process? Well, it is in this parameter phi. You see, rho is the discount factor, and you see that all the parameters of pollution dynamics are here. That's to say that everything is in the solution. And if we go to, we can prove where, under which conditions the transfers are strictly positive, etc. There are conditions, technological conditions there. And when we work with sovereignty constraints, that's the guy respects the two things. then things are much more complicated in the sense that the guy, can you see here, has a problem to solve to determine the optimal transfers, which can prove many things here too. The problem is that we have now appendix with more than 50 pages, so we don't know what to do with this. So I will just show you a couple of results we show with numerical things. I have 3 minutes or 2 minutes. We have solutions, analytical solutions in many cases. I will show you illustrations here, numerical illustrations. So we can, of course, convert our results in terms of pollution into temperature using this very famous equation, and then we compare. This is the calibration. Don't ask me these numbers. I'm not responsible for this. It's Tedlock Temzelides, the guy, the quantitative guy from Minnesota, is doing that. So look at this. Yeah. So what you can notice here is, of course, the differences between. I was a bit disappointed by this. It could be, of course, because of the calibration. This is time. Computing a time trajectory, and the vertical axis is CO2 concentration. And you could see here that, of course, Nash is in green. Nash is much worse. That's no surprise. But what surprised me is of course the fact that the two planners, the restricted and the global, seem close. They are close. Here we have logarithmic utility. It's an illustration of the results we obtain. What we can observe already, I will stop, I think, here, and then I'll show you just the figure on the temperature, and then I will stop. What we can just see is that this is a symmetric case where the gammas are the vulnerabilities. I'm sorry to come back here. I went too quickly on this. The gamma I could be interpreted as adaptation of the country. So we could have even put catching up equation on the gammas here. So gamma I is the vulnerability. So here we study, and figures I'm showing you, we oppose the case where the vulnerabilities are equal to the case where they are not equal. Of course, with larger vulnerability in the south, in Bangladesh. That's basically what we have in mind. And then what we can see is in the case where we have symmetric case, the south is polluting slightly. You see here the dashed line and the dotted line. The dotted line is slightly above the dashed line. Here are the things. So the south is slightly polluting. If we impose that the vulnerability of the north is lower, then of course the north will pollute more. That's the story, and so asymmetric here is much worse. At the temperature, we can have also, you can see the thing. Of course, things change a lot if you move from logarithmic utility. Then you have a lower, if you have a lower elasticity of substitution, intertemporal substitution, then you have less pollution and the results are clearer. I don't have time to present Stackelberg and other things. I think I have to stop here.